Thanks, Vance. So let's begin the workshop. Our first speaker is Dr. Dean Steele. He's an agricultural engineer at NDSU. Been there the same length of time as I, since 1991. His research has focused on irrigation water management and evapotranspiration mapping. And he teaches sophomore level classes at NDSU in both ag systems management and precision ag and ag systems. So he's going to be talking about a new project that we're just starting, and I'll turn it over to Dean and we'll share the screen with you. And you want to take it over, Dean?
Okay. Are you seeing a screen with a green background slide? Okay, good.
Yep.
So yeah, thanks for the time to talk here and the opportunity to present. So we're talking about a project that's kind of originated out of building NRCS technical capacity. And so sponsorship, this is coming out of a conservation collaboration grantor agreement. Christy Fisher and Erica Althoff approached us about developing NRCS technical capabilities. So we've also got Jordan Thompson Larson, who assisted us with soil sampling that you'll see a little bit later. We've got 3 farmer cooperators, and I'm not sure if any are in the audience, but so far we're just calling it Site 1, 2, and 3, and then the North Dakota Ag Experiment Station. It's kind of a collaborative project here between some folks here at NDSU and then the University of Nebraska-Lincoln, Tom Shear and myself. Shinwa Jia, I think, is in the audience here. He works in drainage and hydrology and also some irrigation work. Paulo Flores is a precision ag specialist. And Sheldon and Don are research specialists, and Matt Blum is an intern with the NRCS working with us. On the University of Nebraska side, Christopher Neal developed a evapotranspiration modeling tool based on remote sensing that can be used for irrigation scheduling. Derek Kieran is a irrigation engineer, and Trenton Franz is a civil engineer working with us on some geophysical characterizations. So, and Christy and Erica will talk about this at the next session or next presentation, but their environmental quality incentive program supports conversion of conventional irrigation systems to variable rate irrigation. As part of that, they want irrigation water management with soil moisture monitoring on telemetry so that people can read sensors in the field, and to do that for 3 years following their conversion. So just a little background on, if you look at all the layers of information that can go into managing irrigation, if you look at this green layer, that would just we can call that a uniform irrigation or uniform crop, if that exists, right? But it would be just a case where uniform irrigation, maybe we'll say we'll apply 1 inch of water across the whole field. If you can control the speed of the irrigation system, we'll move up to the upper left here, and then you have what we call sector control. So you slow down the machine, you apply a deeper or greater amount of water, and then you speed up the machine at different angular positions, and that would be a lighter application of water. The NRCS is pursuing the idea of zone control in the upper right. So not only do you have the capability to speed up and slow down the irrigation system, but you have control of individual sprinklers or banks of sprinklers to achieve this kind of ring and sector kind of control. So that's what we're looking at here. So the need for this project came out of the need for NRCS personnel to build their technical knowledge, and this is going to spill over into producers and crop consultants and irrigation dealers. We're trying to target all those audiences. With kind of on the right-hand side, there are some topic areas of irrigation water management, variable rate irrigation. We're going to be assessing sensors that are commercially available and some of the software settings and setup and installation kind of procedures there. And then also looking at some of the remote sensing products for irrigation water management. So kind of 2 thrusts of the project are to evaluate these irrigation water management services and technologies in terms of soil moisture sensors, and we'll show you what we'll kind of use as a reference or comparison. And then also the same for the remote sensing imagery. And we'll also, the second part is to evaluate these watering prescriptions. By prescriptions, we mean the map of irrigation depths, like that kind of checkered map that could be downloaded into an irrigation controller and tell the machine what areas of the field need more or less water. So we have this group from the University of Nebraska, and they're using or have developed what I would call a research grade variable rate irrigation map. And then there are commercial services for prescriptions or variable rate irrigation maps that we'll look at and compare with the one from the University of Nebraska. So here's a couple ways we can schedule irrigations. One is a kind of a water balance approach, and we just look at this box on the right as a volume of soil. Typically the root zone, maybe a little bit deeper, but if you look at the inputs to that box, and one would be rainfall and another irrigation, those are inputs. Evapotranspiration is an outflow, or we say a water removal or withdrawal from this soil root zone. Consists of evaporation from the soil surface and transpiration through the canopy. I put water loss here down at the bottom, implying that it's deep percolation, but we could also have surface runoff or lateral movement, you know, to the left or right in this box. S represents a storage or an amount of water in the profile. So we'd say storage at time 2 on this equation is going to be, we could estimate that as storage at a previous day or previous weeks, S1, plus, you know, the storage would be increased with rainfall and irrigation amounts, and it would be decreased, or so we'd have to subtract off the water losses and the ET. So we can use this as a scheduling tool. And in fact, that's the heart of the irrigation scheduling by the checkbook method, either, you know, in paper copy or online at the NDON website, or we've got a spreadsheet version. So what I did here, down on the horizontal axis of this chart, I've got the dates of the year. So that's in 2020 from May 1st through the end of September. Vertical axis is a soil water deficit or management allowed depletion. What I'd like to think of here is that when you're at 0%, there's like the profile is full. There's no more room for water to be added to the profile. I put in here corn at Oaks, looking at an emergence date of May 15th with a soil. I just kind of said, okay, we're going to try to run a model here with a 12 inches of a fine sandy loam, and then deeper than that, it's going to be just sand. So not a lot of water holding capacity. And as we start out the season, we're going to assume that we're at field capacity or the soil profile is full. And then as the crop emerges, you see the water line kind of goes down here as the crop uses water. And so we're drying out the soil. Wet is on top. So we get some rainfall or irrigation here on the bottom. That's on the right-hand axis. So we got some events, a little over 2 inches, kind of early June here. A little more about that, I don't know, 18th of June or somewhere in there. Some rainfall events refilled the profile, and then it jogs up and down depending on rain and water use. So I think in Oaks on this model, we would, well, NDON indicated about 18.5 inches of rain in 2020. And then these kind of checkered or striped bars here represent, I just put in some irrigation, 6 inches of irrigation to try to keep the soil water deficit above this maximum or this red line. So that's kind of our target to keep the soil irrigated. Another approach to water balances, and this will fit into, so where we're going with this is to do this on a spatial basis, because these methods are kind of described or, you know, developed for one point in the field, but then how do you apply that over a whole field? So another approach besides a mass balance is an energy balance, and we look at a conservation of energy. And the idea here is that you get some, I've got RN here as net radiation. So you've got the sunlight coming in, some of it gets reflected, so there's a little bit subtraction there, but a net radiation, and so you've got incoming solar radiation. Some of that energy is going to go into what we call H, or a sensible heat. That means we're going to heat the air. Okay, so it's going to warm up the air temperature, right? Some of that energy is going to go into the ground, so it's going to transfer a soil heat flux. And so then we assume that some of the energy is going to heat the air, some is going to heat the soil, and the rest of the energy is going to be used to evaporate water. Whether that's from the soil surface or through the canopy, we just lump that together into evapotranspiration. So that's an energy balance approach. So the folks at the University of Nebraska developed models, and we used an energy balance model in the Devil's Lake area on the Devil's Lake Water Utilization Test Project a few years ago. So this is kind of similar. They're using multispectral imagery, which would be like a red, green, blue aerial photo or satellite image, and then some shortwave bands in there. One of the keys is to have a thermal image so they can get an idea of the temperature of the crop or temperature of the surface. And so they're using that information. They're using weather data, maybe like a previous irrigation map and some previous measured soil water content. And they've got some static inputs down here at the bottom, which would be kind of the soil and crop type and pivot characteristics and so forth. So they put all that into the model, and they're using what they call a reflectance-based crop coefficient to help predict water use. So you probably heard of a normalized difference vegetation index from remote sensing, kind of a greenness index for a crop. In Nebraska, Christopher Neal and his team have gone with what's called a soil adjusted vegetation index, which is similar to NDVI, but it's got some adjustments for bare soil. And then they use what's in the center here is called a two-source energy balance. So when we used the modeling up in the Devil's Lake area, it was kind of a one source, or we just assumed the surface was crop. Well, in the two-source energy balance, they're kind of trying to separate out water loss through the soil and water loss through the canopy, which is especially useful early in the season when you have incomplete cover. And then they're using some soil water balance models, and all of that to produce an output is to predict a soil moisture content, and then that feeds into a new prescription for the field. So that's kind of their process for developing a kind of an instruction set for the irrigation machine as to where to put water and how much to put in the different locations. So we'll take a look at some of the work that we're doing and where we'll be going. Trenton France gave me this slide. He's using geophysical sensors, and here's some examples, and there are more of these types of things. And you're probably familiar with the electrical conductivity type sensors. In the middle, there's a gamma ray detector, typically used for assessing the density of the soil, and you can get at soil, properties. On the right's the Veris, another electrical conductivity sensor. So he came up from Lincoln to the 3 different field sites, and on the left, he's got a cosmic ray neutron probe. This is a passive sensor. It's not generating new neutrons, but measuring neutrons in the environment, and that's going to give an idea of water content on a large area. In the center, in the back seat of his truck, here's a gamma detector, and that's a passive sensor as well. He's not shooting out new gamma rays, but he's just measuring what's ambient in the environment. And then on the right-hand side, he's got a kind of a salinity sensor on a sled. So we'll see him here going up and down the field and just kind of pulling it along with a little sled there. He's going about 10 miles an hour, and he said he was going at about a 20-meter swath width here. Got a little wind in the background, apologize for that. So he's going up and down the field. I think his swath is probably a little greater than 20 meters, but just based on the size of the field and the number of passes that we saw there. So let's take a look at, kind of some of his results. But first, I guess I should put in a plug for Paula Flores, who did some topographic surveys. This is an elevation map of one of the field sites. Erica Altoff did a ground-based survey with a real-time kinematic GPS on an all-terrain vehicle. So we got some topography data for the site. Here's Trenton's work, and I won't get into a lot of the results here, but it's his electrical conductivity survey, and you can see him driving up and down the field and then around the edges of the field. As a result of that, he gave that and the other data sets that he gave us some sampling points to go out on the field and do some kind of calibration. So we're trying to characterize these sites, and probably a lot more characterization, in a research mode here than, what a producer would, go in and do. But here we are, there's Jordan on the right pushing the soil probe into the ground, and we bring the core back out. We're trying to sample down to 3 feet. We bring it over on the tray on the pipe here and section it out into different lengths. And bag it up and bring it into the lab. And as a result of those samples, what we're doing is we're getting bulk density, and the bulk density of water is 1. So that's just a reference point. It kind of increases from about 1.4 to 1.6 at most of the sites. The red bars are standard deviations. I'm not going to spend a lot of time on that, but here's volumetric water content. You can see kind of near steady at 20% in the first site. So these are sites 1, site 2, site 1 for 3 different depths. Sorry, I didn't explain that well in the last one. Site 2 is in the middle, 3 bars for the depths 0 to 1, 1 to 2, and 2 to 3 feet, and so on. So it's just kind of telling us the water content's decreasing as we get into the coarser material down below. We're also looking at taking these samples and doing some further lab analysis for field capacity, permanent wilting point, electrical conductivity, and some others in there. Got EC in there twice. But so here's some sensors that we're looking at using. The Acclima sensor is what we would use in a research kind of setting. It's time domain reflectometry, and there's some other commercial products available that have sensors. And so we're going to we purchased some of these, and we're getting others, and we'll subscribe to the subscriptions with telemetry and monitor the soil in the field alongside what the farmer's doing. As far as the variable rate prescription maps, there's again some commercial services available in there, Reinke and Lindsay and Bally, and there are others. Series Imaging is one that does aerial photography. I believe they fly at about 10,000 feet. And give aerial imaging as a subscription service. And then the University of Nebraska-Lincoln, this is their kind of their spatial evapotranspiration modeling interface is their acronym for this project. So just some of the results we anticipate, we're just getting started this fall, some training opportunities for different groups, sensor performance, and then the prescription map comparison. So if you look at training opportunities, there's quite a broad audience that we hope to reach. And I won't read everything there, but here's kind of an idea of sensor comparison. So it's the same chart as you saw before with the checkbook method, 2020 corn at Oaks, and same kind of soil and weather and that kind of information. But what I've added on here is kind of a hypothetical data set. If we had a soil moisture sensor, we could compare the diamonds, the blue diamonds here as measured values against some kind of model. Or we could measure, maybe 2 or 3 different sensors at the same time and see how they line up with a model like this or with each other. And that would be some comparison of sensors. So we might ask questions like, does a particular sensor tend to read high? Does it tend to read low? Or does it track pretty well? Is it strong in the gravel ridge on the north edge of that field? Or is it doing pretty well in the low spot where it tends to be a little wetter? So we can kind of get an idea of how well these sensors perform. And we've got to look at, installation procedures, managing the data sets that we're going to get in. And then, as I mentioned, the accuracy kind of comparisons. The prescription map comparisons, I really don't have a graphic here, but I think, I was learning how to use these and convey that to other people in our audiences, how to manage the data, and then comparisons to this University of Nebraska model. One of the measures of comparisons could be a water volume comparison. So I put in a volume difference. This is like on a whole field basis. Volume of water prescribed by service X, whatever vendor that might be. Subtract that from the UNL model, volume. So in other words, does a prescription service tend to predict higher water amounts are needed, or does it predict lower total amounts needed? And we could do this on an event basis or on a seasonal basis. And then we might want to look at spatial variability and say something or ask questions like, does one of these services tend to require, higher amounts on the gravel ridges or the low areas and this kind of thing. So that's kind of where we're going with the project. And I think I'm pretty much done here. So I would entertain questions or leave it to Tom or Lance if there are, how they want to moderate this. So thank you very much for the time and the opportunity to visit.